Hello. So in this video, I'm actually just going to cover or really talk about two quintessential functions that are used as counterexamples in lots of contexts. But for our sake, these are sort of classic counterexamples to types of convergence. So both of these functions converge to zero almost everywhere, which, believe it or not, is actually a technical math term, but you can think of it as everywhere but at most one point in this particular case. That's not the actual real definition of it. But regardless, so this one will converge to zero everywhere. This one will converge to zero everywhere except zero when x equals 0. But it does so point-wise. And in fact, this one does not converge uniformly at all. This one also does not converge uniformly. And in fact, this one is sort of a little more interesting for other reasons too, but this one has interesting connotations with integration, as does this one. Regardless, I'm actually going to be doing these by, so I gave the formal analytic definitions, but these things are both much easier to understand using their geometric interpretation, i.e. looking at what they look like as a graph. So I'm going to go through them and sort of draw the graph such as I can. I'm not an artist, bear with me, and mention sort of the important bits here. So this function here, this is actually a variant of what is called the moving bump function. And yes, that really is what it's called. So the actual moving bump function is a nice, smooth, infinitely differentiable function. This one clearly isn't, because I jumped from 0 to 1. But to write down the actual moving bump function is a little more, not a lot more, but a little more than we really need to jump into in terms of the actual function definition. Regardless, think about, so look at what this is. This is just a function that is 0 a bunch of places and 1 between n and n plus 1, okay? So if I draw, I'll use this color. So if I draw one of these things, so first of all, let's assume n is, in this case, 0 or larger. So when n equals 0, let's say, just to be clear here, so let's look at, let's say 1, 2, 3, 4, etc. And let's say this is 1, 2. All right. So when n equals 0, this says it's 1 between 0 and 0 plus 1. So it's 1 here, including the points. And then after that, it is 0 everywhere else, right? So I have an open hole down here, then it is 0 to the right, sort of writing blue on blue here, so it's hard to see. It's also 0 on this side, with an open hole there. Okay? So this is n equals 0. So that's the first of the sequence. Now if I go to the second of the sequence, i.e. n equals 1, then that tells me that it is 1 between 1 and 1 plus 1. So between 1, which is here, I'm going to draw it slightly higher just so I can write it in. But it is just equal to 1. It's 1 here, but everywhere else, like down here, it is 0. Which again, this is really 0, but I'm drawing it lower so we can not have a mess of marker. So it is 0, I'm just stacking, that's all. Right? So this is n equals 1. And hopefully, last but not least, hopefully this will help see the pattern. If I do n equals 2, right? So it would be between 2 and 2 plus 1, so between 2 and 3, it is again 1, and everywhere else, it is 0, which again, I'm drawing slightly off the axis just so we can see them stacked. Okay, so this is called a moving bump function, or a variant of it, because what's happening is that as n increases, I'm taking this function and I'm just moving it to the right. See? So as n goes to infinity, I basically have the exact same function, I'm just moving it one integer to the right, but because obviously there are infinitely many integers, there's nothing fundamentally different about this function at any point, at any stage of iterating n, right? The only real difference is where my axis is, really, right? So if I think about like the integral of this function, well, the integral of all these things is just 1, right? Because the integral here is a 1 by 1 block. The integral here, 1 by 1 block. Integral here, 1 by 1 block, right? For any n, it's going to be a 1 by 1 block between n and n plus 1. So if I think about what, for example, for this one, if I did something like the limit as n goes to infinity of the integral from 0 to infinity fn of x dx, well, I can't interchange these two because I don't have, right, so here fn, I mean, this hopefully is somewhat clear, but I should say it anyway. Fn of x converges to 0 pointwise because pointwise, remember, it says fix x, so if I gave you pi, right, and then I have to find a big enough n so that for any little n bigger than that, it's going to be 0 all the time. Well, as long as I pick something where I've moved the bump past that integer value, or really the next integer value, then the bump will keep going that way, right? And I'll be 0 forever after. So the fn of x goes to 0 pointwise. But if I think about this part, the integral of fn for every n is 1, right? So this is really the limit as n goes to infinity. The integral of fn dx for every n is 1, which means this is 1. So this shows that we can't interchange, right? Because if we interchanged and replaced fn of x with 0, I would get the integral of 0 is 0, limit as n goes to infinity of 0 is 0, not 1. Okay? So this function, the variation on the moving bump function, is a great counterexample for things like integrating, but also for this idea of pointwise versus uniform convergence, convergence for fn of x going to f of x, right? Because this thing keeps moving, so pointwise, I can wait for it to move past that point and I'm good. But if I can fix the n and look at any x I want, well, then I could always find an x that's in the bump and thus not 0. Okay? So I would encourage you to try to write a proof saying, like an actual, real, honest, rigorous proof saying that this is not uniformly that it doesn't, fn doesn't uniformly converge to 0. There we go. Okay? So now let's look at this other one. So this one is often referred to as the escape to, sometimes it's specified, sometimes it isn't, vertical infinity function. Okay, so what's happening with this function? This one's a little bit harder to see just by looking at it. That one, right, I can see kind of nicely it's 1 between these two values, 0 everywhere else. So I'm going to give the picture and encourage you to do some iterations beyond what I've written to convince yourself that this is sort of the right thing. So let's look from 1 to -1, and just because I'm going to need the space, I'm going to write this as a little bit lower, 1, 2, 3. So it's not exactly even left, right versus up, down. Actually, still use blue. All right, so when n equals 1, what happens? Well, I have 1 plus 1x, so it's just x plus 1. So that's the x function, right, slope of 1, but shifted left 1. So it's going to go from here, right, negative 1 over 1 to 0. So it's going to go from here to here. It's going to look like that. On the other side, when n equals 1, I'm going to get 1 minus x for 0 to, again, 1. So from 0 to 1, it's 1 minus x, which starts at a y-intercept of 1 and goes down. So it's going to look like this, where the open hole from this side is closed by the closed hole from that side. And then it's 0 everywhere else. So it overlaps the axis all the other places. Okay? So this is, I should also say, this is also sometimes referred to as, because we don't have great imaginations, the tent function. This is another common name for it, which maybe is a little clearer what that's going to mean in a second. Now, if I plug in 2, so I'm going to get 2 plus 4x. So I'm going to have a high slope, but it's going to have a high slope hitting at 2, and it's going to go from negative 1/2 to 0. So what happens is I get cut in half here, and it goes up and hits 2. So it's going to go from here to there. And somewhat unsurprisingly, I'm going to get something of a similar nature on this side, which I think I actually need. Forgot to write the other piece here. Square. So I'm going to get same idea. So this was negative 1/2. And this is going to be positive 1/2. More or less. So, and again, I should record this. So this is n equals 2. So here, that sequence was 0 and on. This one I'm doing 1 and on, just because otherwise it would look really weird. So this is n equals 1. And last but not least, if I do 3, same as I'm sure you can sort of predict now, it's going to go up from 3 down here at, say, negative 1/3 and 1/3. So it's going to look like that and that-ish. And this is the n equals 3 case. Okay? So the idea here is that I have something that is growing vertically at the same time the base is collapsing inward, right? And so I can calculate the area of these shapes if I want to, and if you do, you'll note that the area is also collapsing, right? So this is an example where I do get some sort of area going to 0, even though, and the function going to 0, but this still won't converge uniformly, right? It converges pointwise, because if I fix an x, I can make the n big enough that I pull in enough that I'm at 0. But if I fix an n, I could go left, towards 0 enough that I'm inside the tent, and then it's not 0, right? It's really far away. So again, I encourage you to formally, rigorously prove it's not uniformly continuous and that it is pointwise continuous. Those are very good practice problems, but that is essentially will be the case. I will also point out, though, that I picked a height that was sort of easy to draw, right? So it goes from 1 to 2 to 3, but there's nothing stopping me from manipulating these functions a little so that instead of going 1, 2, 3, it went from, say, 1 to 4 to 9 to 16, or I could do like 4th powers or something, right? So it would go from 1 to 16 to 81, etc. And if I had done that, so if I did, say, 4th powers, I would have gotten a height of x to the 4th and a width of whatever it would have been. So what? 1 over n, so twice that? Yeah, it would have been twice 1 over n. So 2 over n wide and n to the 4th tall, so I would have gotten like 2n cubed as the area, meaning that I could build this so that the area goes to infinity or goes to 0. Or I could even build it so it stayed static, right? Because all I need to do is change the height while the edges come in at the same rate that they are right now. So this is a great way of building something that sort of has a limiting behavior like this that does basically whatever you want, right? Like you can have, okay, the limit of fn of x goes to 0, but the limit as n goes to infinity of the integral of fn of x, even across some, -1 to 1, is, diverges to positive infinity, or goes to 0, or goes to 15, or whatever number you feel like choosing, right? So this is another sort of classic counterexample because it gives you sort of a nice visual way of building these kinds of functions, okay? So like I said, I encourage you to go ahead and sort of practice by proving these both converge pointwise to 0. This will not converge pointwise to 0 at 0, but everywhere else it will. But also show that it does not converge uniformly to 0. And this one also does not converge uniformly to 0, even if you ignore 0 itself. Interestingly, though, you could show that this one converges uniformly to 0 on, say, negative infinity to epsilon closed, negative epsilon to infinity. Meaning that if you sort of cut out an epsilon slice around 0, then you could get uniform convergence. And that might be worthwhile trying to prove as well. Okay? So with that, we are done. Classic counterexamples.